Welcome to the Serverless Innovation Day. My name is Silo Casing, and I'm here to talk to you about scaling containers from 1 users to millions. I'm a developer advocate with the ECS service team, and today our agenda is going to be pretty much this. We're going to go a little bit over the ECS overview, give you a bit of background about ECS if you're not familiar. We'll talk about some scaling considerations, and also about some performance and optimization tips that you can use in order to get your applications to very large scales and very large numbers. There might be those in the audience who may be new to AWS. So here's a quick refresher on the Amazon Elastic Container Service. ECS is a fully managed native container service. There's no control plane, no middleware for customers to install, manage, or upgrade. It is a highly performant and scalable service. ECS works with EC2 across all regions, on outposts, local zones, and wavelength. You can also deploy your containers on ECS on AWS Fargate, which is the rapidly growing serverless compute engine available in AWS. And you can also, if you really want to, deploy ECS on your own customer-owned host outside of AWS itself. When we say ECS operates at massive scale, we really mean it. The numbers speak for themselves. ECS serves over 2 billion task launches every single week with tens of thousands of API requests per second across all AWS regions. ECS has day one support for any new region and will be available with new region launch. 65% of all new container customers at AWS are using ECS across all customer sizes and segments. And it's not just the horizontal scale, but ECS's power is to support workloads of any size, anywhere, at any speed. We are seeing fast adoption of GPU and high memory workloads, indicating that customers are using ECS for larger, resource-intensive workloads as well. This slide might look a little bit complicated, but it demonstrates ECS's scale capabilities with increased limits. This is an example of an actual customer workload scaled up to 2.3 million virtual CPUs across 12 clusters. The powerful simplicity we provide helps customers to really use the resources that they need. 45 minutes to scale to over 2 million virtual CPUs, and more importantly, about the same amount of time to scale down to minimize costs so that you pay just for what you need and nothing more. The ECS powerful simplicity enables a diverse set of customers of different sizes and stages of their cloud journey to innovate and focus on bringing value to their customers. Some examples: Capital One for digital banking and finance, Disney Plus for streaming, Instacart to have digital native and grocery delivery, Ubisoft for the multiplayer gaming, Okta in the identity services market, and many, many others as well. And it's not just our external customers. ECS is the building block for a wide range of innovative Amazon services which are built on top of it. You may be quite familiar with some of them. Traditional database services like RDS, modern AI and machine learning services like Poly and SageMaker, transactional services like Amazon Translate, and large data and ETL services such as Batch. Over the year of 2022, we improved Amazon ECS scheduling to enable you to deploy each service at a rate of up to 500 tasks per minute when using AWS Fargate capacity, and 500 tasks per minute when using EC2 capacity. For AWS Fargate, the deploy rate is 16 times faster than the previous year, and for EC2, the deploy rate has quadrupled. Of course, there are more things that go into application deployment than just the ECS task launch rate, of course. For example, container image size, pull behaviors, load balancer configurations, health checks, and many others as well. We'll be walking through some of these considerations and best practices shortly. The linked blog post at the bottom contains a set of benchmarked applications across different configurations for ECS on Fargate and on EC2, where you can dive deeper into the details. Whether you're designing a brand new service or scaling to a service to meet new customer demand, thinking about how you will scale your service can be a complex topic. Often your scaling numbers are derived from business demand, handling customer interactions, responding to automated events, or running models to make decisions in real time. Engineers tend to translate these into application-specific units like expected throughput, transactions per second, the number of jobs processed per minute, how many messages processed every second, and more. The following section will describe how you can use these scaling units, whose performance varies from application to application, and use it to derive the appropriate scaling units on your underlying compute platform, ECS. So before you dive into the ECS-specific considerations, we recommend that you take a step back and really have a deep look into your applications. Start with looking at the scaling resources requirements for your applications among the dimensions such as CPU, memory, GPU, network bandwidth, and storage. Remember that other resource consumption from your application, like network bandwidth or disk utilization, may be the resource that is limiting your container's throughput. With your testing, you can define an application profile. This will be your unit of deployment. Typically, one or more of the resources could be a performance bottleneck. You should test a single application container to understand your application behavior under different load scenarios. Tune and tweak your application to find the optimal configuration for your application profile. Now, map these scaling considerations to an ECS task. An ECS task is how you define your application containers to run on ECS. You also need to understand how many tasks you will need to scale out to support millions of users. Once you understand the general design of your service and the number of tasks you will need to launch, you can begin to evaluate which AWS limits will need to be updated to support your use case. You may need a variety of limit increases depending on the scale and the dependencies of your application. Our customers often ask, what is the best compute choice for my application? The answer for that is always start with Fargate, unless you have the following which applies to you, in which case I would recommend that you use ECS on EC2. And these include strict requirements for owning the actual EC2 instances. For example, install custom security modules or logging modules or monitoring modules for compliance. If you need a specific instance type, or you need GPU support, or you have a specific platform architecture which is currently not available on Fargate, then you should use EC2. If you have CPU or memory requirements which are above or beyond the current available options for today on Fargate, or if you need a network mode for your containers which is other than AWS VPC mode, for all those cases, you should use EC2, otherwise use Fargate. So let's dive into the specific considerations for operating at scale in ECS, including service quotas, API throttling limits, and troubleshooting, and of course, performance and optimization tips. ECS relies on several underlying AWS services, and as such, you would need to take into account several different aspects of resource limits. It could be at the account level, how many clusters you can provision, how many IP addresses you have available in your VPC. At the cluster level, how many workloads you can run on a single cluster. At the service level, how fast you can scale your service up or down. And at the task level, the memory and CPU resources each task will need. Requesting a service limit increase is a simple process. Using the Service Quotas console, you can submit a request for each specific region and resource that you need to be added. Let's talk a little bit about throttling. There are two types of API calls, synchronous and asynchronous. When we're talking about synchronous APIs, this category of throttling that might occur when you call Amazon ECS APIs while running tasks or creating services. When synchronous throttling occurs, you immediately receive an error response from the Amazon ECS API. When your application initiates API requests, for example, using the AWS CLI or the AWS SDK, you can remediate API throttling. You can do this by either architecting your application to handle the errors or by implementing an exponential backoff and jitter strategy with retry logic for the API calls. You can find more information about the throttling involved and the relevant throttle limits in our documentation. The second type is asynchronous throttling. Asynchronous throttling occurs because of asynchronous workflows where Amazon ECS or AWS CloudFormation might be calling APIs on your behalf to provision resources. It is important to know which APIs Amazon ECS invokes on your behalf. For example, the Create Network Interface API is invoked for tasks that use the AWS VPC network mode, and the Describe Target Health API is invoked when performing health checks for tasks registered to a load balancer. When your workloads reach a considerable scale, these API operations might be throttled. That is, they might be throttled enough to breach the limits enforced by Amazon ECS or the underlying AWS service that is being called. For example, if you deploy hundreds of services, each having hundreds of tasks that concurrently use the AWS VPC network mode, Amazon ECS invokes elastic load balancing API operations like register target or describe target health to register the elastic network interface or the load balancer respectively. These API calls could exceed the API limits and result in throttling errors. The following example on the screen is an elastic load balancing throttling error that's included in the service event message. When these API calls share limits with other API traffic and applications in your account, they might be difficult to monitor even though they're emitted as service events. Proactively monitor your account, and when you see any throttling errors, contact AWS support to raise limits for those. We are continuously increasing these limits and making improvements on behalf of all of our customers on a regular basis. With Amazon Athena, you can create queries and analyze data using standard SQL. For example, you can create an Athena table to parse CloudTrail events and filter for throttling errors. Contact AWS support to raise those limits or ask them for help for exploring alternatives if you see frequent throttling errors. Amazon ECS also emits event notifications to Amazon EventBridge. There are resource state change events and service action events. They include API throttling events such as the ECS operation throttle and the service discovery operation throttle events. These events can be consumed by a service, such as AWS Lambda, to perform actions in response to the event. If you run standalone tasks, some API operations, such as run task, are asynchronous and retry operations aren't automatically performed. In such cases, you can use services such as AWS Step Functions with EventBridge integration to retry throttled or failed operations. So let's look at some performance tips. There are two elastic load balancer health check parameters that affect deployment speed. First is the health check interval. This determines the approximate amount of time in seconds between health checks of an individual container. By default, the load balancer checks every 30 seconds. This parameter is called health check interval seconds. The second one is the healthy threshold count. This determines the number of consecutive successful health checks required before considering a container healthy. By default, the load balancer requires 5 passing health checks before it reports that the target container is healthy. And this parameter is called the healthy threshold count. So with the default setting, the total time to determine the health of a container is 2 minutes and 30 seconds. That's 30 seconds multiplied by 5. You can speed up the health check process if your service starts up and stabilizes in less time. And of course, you have to check and validate that this is the case. To speed up the process, reduce the number of checks and the interval between the checks. So if your service starts and stabilizes under 10 seconds, you can reduce the health check process from the default 2.5 minutes by configuring the health check interval seconds to 5 and the healthy threshold count to 2. And this will declare your service healthy after 10 seconds. You can also speed up load balancing connection draining. This will reduce the deregistration delay from the default 5 minutes for highly responsive services to something more appropriate, which will allow you to scale down your service much, much faster. Amazon ECS first sends a SIG-term signal to the task to notify the application that it needs to finish and shut down. And then Amazon ECS sends a SIG-kill message. When applications ignore the SIG term, Amazon ECS service must wait to send the SIG kill to terminate the process so that you don't, by mistake, kill a working container which is still processing information. The amount of time that Amazon ECS waits is determined by the following Amazon ECS agent option, which is called ECS container stop timeout, which is 30 seconds by default. To speed up the waiting period, you can reduce and set the Amazon ECS agent option to a lower value, which will enable you to scale down your applications much faster. But what about those tasks which are running and parsing or processing information in a long time? For these long-running tasks, you can use the scale-in protection feature. This feature will ensure that tasks are not interrupted while processing data and will signal the ECS API to not terminate the task until the process has completed its work. When complete, the task will signal the ECS API that it is now safe to scale down the task. Keep your container image repository in the same region as your workloads. This is important to reduce the latency in container image pull times, reduce your egress traffic, and optimize your cost. Cache your container images. If you're running Amazon ECS on Amazon EC2, you can configure the Amazon ECS container agent to cache previously used container images. That reduces the image pull time for the subsequent launches. The effect of caching is even greater when you have a high task density on your container instances, which you can configure using the bin pack placement strategy. Caching containers is especially beneficial for Windows-based workloads, which have very large container image sizes. For AWS Fargate, we have some additional and other recommendations. Use large task sizes. This will increase the underlying compute and network resources available, which could improve your image pull and start times. Make sure you optimize your container's image sizes. Smaller images are always better. Track your task launch lifecycle to find optimization opportunities. When launching container images, running startup scripts and other configurations during application startup can take a surprising amount of time. You can use the ECS agent metadata endpoint to post metrics and track application start time from container start time to when your application is ready to serve traffic. With this data, you can understand how your application is contributing to the total launch time and find areas where you can reduce unnecessary application-specific overhead and optimize your container images. There are many instances where AWS VPC network mode is ideal. Sometimes this network mode can inherently increase task launch latency. For each task in AWS VPC mode, Amazon ECS workflows need to provision and attach an ENI by invoking the Amazon EC2 APIs, which adds an overhead of several seconds to your task launches. On the other hand, a key advantage of using AWS VPC network mode is that each task has a security group to allow traffic flow. This means you have greater flexibility to control communications between tasks and services at a more granular level. If the benefits of deployment speed outweigh the benefits from AWS VPC mode, you can consider using the bridge network mode to speed up your task launches. When you have the profile of your application, you remember we did that way back in the beginning of the session? You can plan appropriately to right-size your EC2 instances. Choosing instances that are too large will result in wasted resources. Choosing instances that are too small will result in additional latency for task launches because your underlying ECS cluster will need to scale up the compute capacity needed to meet the demand. When using the bin pack placement strategy, consider using the Elastic Network Interface ENI trunking to place more tasks with the AWS VPC network mode on each container instance. ENI trunking increases the number of tasks you can run on AWS VPC mode. For example, a C5 large instance by default supports running only 2 tasks concurrently. You can run up to 10 tasks with ENI trunking. So let's recap what we went over today. We had a brief introduction to ECS, the scale at which it operates, the scale it can provide to your application. We looked at the considerations you need to take into account when planning your application, how it scales, and where you should increase AWS limits when needed. We also went into some performance and optimization tips and some best practices when running containers on ECS to help you meet the most demanding requirements from your application. Thank you for joining this session today. My name is May Seidel Casing. Please feel free to reach out with any questions, feedback, or thoughts you have on the topic. My mail and Twitter handle here on the screen. Enjoy the rest of the sessions for today.